Hi, I'm Tim Berglund with Confluent. In this episode of the Fundamentals of Apache Kafka, we're going to dive a little bit deeper into how Kafka works. When we're done, you should be able to think a little bit more deeply about the actual code in a producer and a consumer, how those work. You should know a little something about exactly one's semantics. You could talk about the way high availability and durability are accomplished in a Kafka cluster, and you can talk at a high level about how you might secure a Kafka cluster. Here is a minimal producer in Java. Now you'll notice this is just a public static void main method, so very simple standalone application. There are kind of four sections there that are boxed off. Let me talk about those. The first one is configuration. You make a properties object and you give it some configuration. Minimally, you have to tell it kind of like where the cluster is. That's that bootstrap server list there. There's just a list of one address. That's a broker or a list of a small number of brokers in the cluster, so the client has some idea where to connect to and get cluster metadata from. You also have to tell the client the type of the key and the value. In this case, they're both strings, but it has to know how to take your language types, whatever those objects are in your language of choice, and serialize them into the bytes that it's going to send across the wire to the Kafka cluster. And that's what those serializer configurations are there. Next, you create the producer itself. In the case of the Java library, that's a class called Kafka Producer. And you'll note by the time we're done here, there are only two classes in the API that you absolutely need to touch. Kafka Producer is one of those. You pass the config to it and it starts up, and boy, there's lots of stuff happening in there. Connection pooling and buffering and all kinds of machinery that ideally you'll never need to touch. It's just in that producer for you. Next, we add some shutdown behavior. Now, again, this particular application, when it shuts down, the whole JVM is going to get torn down. So it's kind of hard to have concerns about resource leaks, but this is just good hygiene. Make sure when we're shutting down, close down the producer. Finally, we actually send the data and you see the key and the value that we're creating there. They're called key and value followed by a number. Yes, folks, we do write these ourselves. And the other class that you care about besides Kafka Producer is Producer Record. And you see that there. It's also a generic class, just like Kafka Producer is. You have to give it the types of the key and the value, which in this case are both strings. And to create a producer record, you pass it the key and the value and the topic you want to write to. So that's kind of the primitive of producing. It's key, value, and topic. Go to the cluster with that send method. We'll dig in a little bit later. What really happens when you call send? You're probably thinking, okay, it's off to the cluster and we're done. There's a little bit more to the story than that. But in a simple producer like this, you really can just call send and things will get sent. Now let's look at a consumer, but go for a different language just to mix things up a little bit. This is C#. And again, we've got a standalone program. So this is just going to run and consume and then shut down. But let's look at the 5 parts that we've got broken down here. First, again, at the top is configuration. That looks a lot like producer configuration. You have to tell the client where the cluster is. And you notice there's no types here. We'll get to serializers or actually deserializers in just a minute, but a little bit more consumer configuration in that configuration map. Next up in the C# driver, we set up some event handlers. So rather than getting messages back and iterating over them in an imperative way, we say, well, when a message happens, that on-message event, take this action. And you see that genius consumer we've got there. We're logging it to standard out, which actually, I joke, but your first consumer that you write, you're probably going to do that same thing. That's super easy to do. You know it's going to work. It's comforting. You get feedback. So this is actually a great way to get started. There's also an on-error and an on-consume error handler set up there for various error conditions. But that's the way the C# driver works. You set up those event handlers so that later on, when we get to actually consuming, those will just run by themselves. But before we get there, we have to call subscribe. And this is a key part of pretty much any consumer language binding. You have to tell the consumer what topic or topics you want to be listening to. And here we just provide one. You can provide a collection of them. You can provide a regular expression that will cause you to subscribe to all matching topics if you just want to watch the world burn. That's up to you. You can do that. But the point here about consumers is that you can subscribe to one or many topics. If you've got lots of topics that have the same format of message in them, you may want to consume them all at once, and that is perfectly valid. Finally, at the bottom here, you have a while true loop. So that's an infinite loop. It's going to run forever. We're going to poll, and that's all that happens there. We say, hey, consumer, go check to see if there are messages. And if there are, what's going to happen? Well, our event handlers are going to run up above. So we'll be logging those messages to standard out when the onMessage handler runs. So that never stops. And this is typical for a consumer. This is how event streaming software, event-driven software works. When you're reading, you read forever. There's never a last event. You're never done. You just process each one and then wait for the next one. That's very, very typical. Can be a little disquieting if you're used to, say, web programming with the Spring framework. You're normally annotating methods, and those methods get called and they run to completion and they're done, and that's sort of comforting and you feel like that's the right thing to do. But in consumers, you generally do just loop forever and always keep consuming messages. Okay, let's leave the world of the producer and the consumer and look inside a cluster. Now, here is a Kafka cluster with 4 brokers, and I want to talk about partition leadership here. So 4 brokers, we're looking at one topic. Now, probably this cluster has other topics, right? Probably not just a one-topic cluster, but we're not looking at any of those. We're just looking at this topic called, somewhat prosaically, Topic 1. To make the diagram look nice, we've made Topic 1 have 4 partitions, which is the same number as the number of brokers, because, man, that's beautiful. I point that out so that you know there is no required relationship between those two things, okay? I could have a topic with 200 partitions and 4 brokers. I could have a topic with 1 partition and 4 brokers, or 10 brokers, or anything. There's just no correlation between those numbers at all. The slide looks nice in this way. It's easy to kind of see what's going on, but I don't want you to think that those numbers are in any way tied. Okay, look at the top there. That's partition 1 of topic 1. This topic has 4 partitions. Partition 1 has a total of 3 replicas. It has 1 on broker 1, 1 on broker 2, 1 on broker 3. And you probably see that the shading of partition 1 on broker 1 is a little darker. That's a darker color than 2 or 3. That's because partition 1 on broker 1 is the lead partition. Broker 1 has the leader for that partition. Broker 2 and broker 3 are followers, and they behave differently. So if you're a leader, that means you're telling producers and consumers that when someone wants to write to this partition, that producer should actually write to you, should send you the message, and you'll take it and you'll stick it in your partition log because you're the leader. Those writes happen to you. And when you're reading, when you're consuming, that consuming is going to come from you as well. Now, in versions of Apache Kafka after, I want to say 2.5, it is actually possible to read from followers and not just the leader. And there are some very important scenarios, usually in like multi-data center or multi-availability zone cloud deployments, where that enables some kind of cool functionality. But for the first order approximation, for you just wrapping your mind around fundamentals, you can for now think when a producer produces, it produces to the leader. When it consumes from the leader. So that leader is very important. And those followers are just trying to keep up with that leader. When new messages arrive at the leader, the followers will see them and write them to their own logs. So you see each partition has its own leader on a separate broker. That's really cool. What happens when a broker dies, like broker 4 goes away? Well, one of the followers of partition 4, in this case broker 2, will be elected as the new leader. And that's the thing the cluster does automatically. You don't have to think about that. When a broker dies, you might see a timeout in a producer or consume. That's always possible. But that failover is going to happen. We'll have the new leader elected right away, and writing and reading can continue with no loss of data. That's how leader election works in Kafka. Now, when events happen, they can't really unhappen. You can't change the way they happen. Events are immutable. So the things you write into a Kafka topic, those events, those messages, they're immutable. They stay there. You don't get to edit them. But you might not want to keep them forever. By default, they're retained for 1 week. That's out of the box. Download Apache Kafka, install it, create a topic. It's going to have a retention period of 7 days. That is completely configurable globally in the cluster or per topic. Okay, it can be a very short period of time. I recently ran a test with a topic that had a retention period of 15 minutes, and that actually seemed like a good idea. You can set it to infinity. You can never delete data so that it stays in the topic forever if you've got the space for that. This is not really a technical constraint. It's more of a resource constraint and sometimes a regulatory one. This will be a business decision where the legal department might tell you that you have to retain this for 3 years, or you must not retain this for longer than 7, or I don't know, seems like 30 days is kind of a lot. That's a thing where the business weighs in. And it's, of course, an engineering decision too, because you're trading off cost versus various kinds of functionality you might realize by longer retention periods. I should mention, if all of this talk of immutable data and things never going away until some long period of time, if that scares you from a compliance perspective with things like GDPR, please don't worry. Those are beyond our scope here, but of course there are tools and techniques for handling that. People who have to comply with GDPR keep customer data in Kafka. That's absolutely a thing that happens. Again, beyond our scope, but I just don't want you to worry about it. Also, a brief note, remember we talked about those segments before, how each partition is composed of segments? Well, that's how data is actually expired. When the newest record in a segment is older than the retention period, then we can kick that segment out. We can delete that segment. So those whole segments stand or fall on their own. They get expired and fall off the edge of the world as they age past the retention period. Let's zoom into a producer and see what's going on inside there. I mean, you create a producer record and you call send and you think everything's fine and it's done. And honestly, probably everything is fine. But you might want to know a little bit more about what's going on. When you call send, that message goes through serialization. So you've had to configure those serializers. You've had to tell the producer library what the type of the key and the value are. And then that class is going to know how to take that object and turn it into the bytes that it passes on to the partitioner. That partitioner is going to see if there's a key, and if that key is not null, then it'll hash it and use that to determine what partition in the topic that will be written to. Of course, there could be a custom partitioner that's implementing some other logic. That partitioner will know that. That will be the custom partitioner then. That'll do that other thing. But generally, we're just hashing the key, and that sends it on to a partition. That partition is really like a little buffer where those messages get buffered up for a little bit before they get sent across the network. And the trade-off between how much batching we do in the consumer, that is how much buffering we do, how often we flush that buffer, that is the classical trade-off between throughput and latency that always exists in network interfaces like this. There's nothing particularly Kafka specific about it, but it's all tunable. That's all stuff that you can look into in detail when you're tuning your producers. The producer is also potentially waiting for acknowledgement when it sends a message. This is a configurable thing, and so it's a thing that you set a configuration parameter and the producer library just does it for you. But there are really 3 settings. One is no acts at all. That is, send it and don't wait for it to get written. The network transfer across that TCP socket has been successful, but you don't know what happened inside the broker. Did it get written to disk? Is the disk full? Is the disk on fire? We don't know. Anything could be happening in that broker. All I know is I sent it. I'm not going to wait for an ACK. I'm moving on. So this will cause data loss occasionally. Some messages will get lost, but you'll have very low latency on the produce side. You could also wait for just the leader to acknowledge the message. That's that middle case there. So the producer sends the message to the leader, which it always does, and waits for that reader to write it to the disk and then send an acknowledgement. When it gets that acknowledgement, it says, okay, this has been written to a disk in the world. I feel pretty okay about this. I'm going to move on. Your other option is to wait for all acknowledgements. That means all replicas that are up. In this case, you see there are 3 of them. There's 1 leader and 2 followers. Those 2 followers have gotten around to asking for that new message, and they've written it to their own disks, and they've told the leader, hey, I have replicated this, and it's on disk. Everything is fine. And that leader is waiting for all of its in-sync replicas to respond. It says, okay, I've got them. This is now on 3 disks in the world. I'll tell the producer everything's fine. So more latency there, but also a lot more safety. You're not going to lose data that way. Those delivery guarantees correspond in name, although not comprehensively, to the basic at most, at least, exactly once paradigm. So look at the skittles coming into the gears there. The skittles on the left, those little circles with the numbers in them. And I hope they don't get ground up into gears because, skittles taste good. It would be better to eat them. But as those events get processed by those gears in the middle there are 3 ways the processing can take place. They can be processed at most once. That means that some of them might get lost. We'll never duplicate them, but some of them might get lost. If it's very important not to do something twice and it's okay to miss some things, then you want at most once processing. At least once means we're going to make sure everything gets through. In the process of making sure everything gets through, we might accidentally double up sometimes. And there are valid reasons for why that happens. And so sometimes we're going to see duplicates like you see here. You see 1, 2, 2, 3, 4, 5, 6, 6. So it's at least once you're saying duplication is okay. So if the read process for those messages is idempotent, that means that reading and processing one time and reading and process many times are the same. So the second, third, fourth time that you process a duplicate, you're not hurting anything. That's an idempotent process. Think of it like turning on a light switch, right? You enter a room and you walk in, you can't, it's dark and you're kind of groping at the wall and you move your hand up the wall and you bump the switch up. The light is on now, right? What if you do that operation again and you bump the switch up again? Well, the light's still on. It's fine. That operation is idempotent of flicking that light switch on. And so that would be a good candidate for at least once processing. Now, exactly once processing means that you're not going to miss messages and you're not going to process duplicates. Let's talk about that a little bit. Now, Kafka has provided this since about the spring of 2017. That's Kafka 0.11. So it's been a while now. Now, you may bump into people, and maybe you're one of these people yourself, who think that this is impossible in distributed messaging. There's this robust computer science result called the atomic broadcast problem that proves that exactly once is impossible. Well, no. And what the atomic broadcast result says is that exactly once delivery in a distributed messaging system is actually impossible. And so messages may get delivered more than once, and there's nothing you can do about that except drop back to at most once, right? So if you're not at most once, if you don't want to miss messages, you might send a message twice. What this transaction API does, and by the way, at the API level, this is an enhancement to the producer and the consumer. It looks exactly like a database transaction API. You begin a transaction, you do your writes, you commit the transaction at the produce side. Same side at the read side, you begin, do your reads, commit. So it fundamentally is a transactional API, and what it does for you is give you a guarantee that you will only process every message one time. Yes, some of those messages may be delivered more than once, but there's this switch in the producer that causes it to produce idempotently, so we're able to detect those duplicates, and some other things with another topic that helps keep a transaction log. The details are fascinating and frankly pretty available online. If you want to Google, you'll find talks from some of the engineers who wrote this stuff that talk about how it works, but this is a way that you can get exactly once processing semantics from a distributed stream processing system. And doing this yourself with the producer and the consumer is not too hard. Again, it's not too crazy of a thing to get that done, but it gets even easier when you start looking at tools like KSQLDB and Kafka Streams. Then it's just a configuration parameter that you switch on. Let's dive into consumer groups in a little more detail. We have here, again, the canonical Kafka architecture diagram emphasizing some other components. There are those two producers. Each producer is producing to its own topic, and each of those topics has 3 partitions. There's one consumer group with 2 instances of the same consumer. We're going to call those instance A and instance B. So that's the same image, the very same program, just deployed twice. Now, that consumer is consuming both topics, X and Y. It's consuming all the messages from both topics. Now, let's look at how the partitions are assigned. And this partition assignment, by the way, is done cooperatively between the consumer group and the cluster. They just do this automatically. You never think about it. You don't have to take any action to make this happen. So partition 0 and 1 of topic X, those go to consumer A. Partition 2 of topic X goes to consumer B. It's going to do its best to allocate these fairly for each topic. And since there are 3 partitions and 2 topics, somebody's going to have more than somebody else, and that's just kind of how it works. And unfortunately for poor consumer A, that's exactly how topic Y works out as well. Partition 0 and 1 get allocated to consumer instance A. Partition 2 gets allocated to consumer instance B. Now, what happens when the composition of the group changes? To make this a little easier, let's simplify things and go to just one topic with 4 partitions. Initially at the top here, we've got a state where the consumer group has 2 instances, and so each instance gets 2 partitions. You get partition 0 and 2 on instance A, and 1 and 3 on instance B. If we add an instance, so we've scaled that consumer out elastically, just at runtime, we just added an instance, the cluster says, oh my, I have to reassign partitions here, and it does. And we see only consumer instance A gets 2 partitions, instance B and C get 1 partition each. And that happens automatically. You don't have to do anything. If one of those instances fails, well, the partitions that it's responsible for, which in this case are 0 and 3, those get reallocated to the other instances. So at the bottom, we have a fair scenario again. Now, that might actually be trouble, right? That there's only 2 instances. That failure might be very bad. And it may be that we're not able to keep up now. The messages are coming too quickly, and the computational expense of each consume operation is too high, and we'd better get another instance deployed as quickly as possible. But Kafka does that reassignment for us, and we don't have to do that ourselves. Now, one thing the consumer API doesn't do is it doesn't migrate state. So we're not looking at the code and what's happening inside consumers, but typically most interesting consumers are stateful. So you're going to remember something about messages that have come before. Maybe you're grouping in a window, and over the last 5 minutes, grouping up a bunch of values and running some reducing function over them, like an average or something. Well, that's all stateful. You have to remember things. And that state that had been in instance A when it died, well, it didn't go anywhere, right? Unless we were doing something with that state, the consumer API didn't help us migrate it. So this is a thing that Kafka streams and KSQLDB do for us. They do all that, frankly, fairly thorny state management, all internal to the API or internal to the KSQLDB server, which is a great thing. We'll cover those more later. I just want to point out that state is a thing that you'll have to think about here if you're counting on elasticity and fault tolerance in the consumer API. Now let's dive in now to compacted topics. This is a thing that's configured at the topic level. That topic on the top, let's just kind of look at that. It's got offsets, 0, 1, 2, 3, 4, those individual offsets, right? And keys and values. Now, if you just let your eyes go along the value, you have V1, V2, V3, V4, 5, 6, 7, 8, 9, 10. Those are all unique up to 17, right? Unique values. But there's only 4 keys. K1, 2, 3, 1, 2, 3, 3, 3, 1, 4, 2, 3, 4, 4, 2, 3. There's 4 keys that are unique. Now, if this is event data, like I always like to talk about my smart thermostat network, phoning home every minute, reporting temperature and humidity data and metadata about the household power supply and whatever else it wants to talk about in those values, those keys could be the unique IDs of those devices. So I've got a smart thermostat in my hallway, and that has a unique ID, and every time it phones home, that event gets stored with that key in the log. I might want to keep all those events, right? That might be useful to me to keep that whole history. So I'd want that regular kind of log. If, on the other hand, I wanted to log changes to my user profile, I log into my smart thermostat network, and I'm going to change my middle name and my profile picture and my zip code. Well, if I'm storing that kind of thing in a log, and K1, K2, K3, K4, those are not device IDs, but user IDs, well, I may not care about previous states of my user profile. I just want the current state. And that's why I use a compacted topic. So a compacted topic does what it sounds like. It takes all those keys and just takes the most recent version of each one. So if we turned that top log into a compacted topic, then you'd see K1 would have V10. It wouldn't have V5, wouldn't have V2, wouldn't have V1. Those are previous values of K1. K3 would have V17. It wouldn't be 9, it wouldn't be 8, it wouldn't be 4, just the most recent one. So that's a very important thing that you can do with a topic. If the topic is storing really entity data, and you're really only interested in the most recent state of that data and not previous values, you can save lots of storage by making that topic a compacted topic. How do you troubleshoot a Kafka cluster? Well, great question. The classical answer is, of course, log files. This is a distributed system. Each node is going to have a few of its own log files. You can look through those. You can set up centralized logging and get that all in one place if you want. Of course, all those tools are available the way they normally are. There's also Confluent Control Center, which is a commercial offering, a part of Confluent Platform, that gives you at-a-glance insight into what's going on into the cluster and really is kind of the purpose-built Kafka cluster Confluent platform optimized monitoring and management tool to give you insight into what's going on in your cluster and how you could best keep it healthy. Now let's talk about security, starting with encryption. Now, Kafka will encrypt any data in transit. So that's client to broker, broker to broker, broker to zookeeper. Those are basically your connections, and we can encrypt all of those with SSL, you managing keys in whatever way you like to manage keys. That is all fairly doable, and there are great examples on how to get that done. Also supports authentication and authorization. So in order to establish, hopefully, an encrypted connection from a client, you have to present a principal name and a password, and then that principal name has to be authorized to do the thing that you're trying to do. And the cluster itself manages those access control lists to map principles to capabilities. There is not encryption in data at rest, so data stored in partitions in those log segments of partitions. Out of the box, that's not a thing, and so people do one of two things. One is they deploy full disk encryption systems so that everything on the disk is encrypted, and the other solution is to do that at the application level. Typically what will happen there is that you'll write a wrapper around the producer and the consumer libraries that does that encryption and handles the key management and all of that stuff. You're going to have various enterprise standards for how you want to do that. So that'll get done at the client level. So before the data even gets to the wire, before it can possibly get to a topic or a partition or a segment, it will already be encrypted. So that should give you a little bit of a better idea of how Kafka works in detail. We've drilled down into brokers and looked at how replication works and leader election, taking a look at what's going on inside producers, how consumer groups work, some really important things there, and giving you a rough idea on how Kafka thinks about security. If you're interested in some further reading on any of these topics, here are some links you're welcome to pursue. It's always good to dig into this stuff in more detail as you're interested. All of this, though, will prepare you to understand the parts of the ecosystem as we expand outside of broker and producer and consumer. What's in Kafka as a platform beyond those things? We'll look at those next.